welcome everybody to this video game programmer uses the STL, and you will never go. You ever guess what happened next? Well, even I can't pronounce it. So about this title, started as a joke. You know, I make jokes on Twitter sometimes, and sometimes people like them, and I kind of take that as an encouragement. So I thought about, like, maybe I should have done something, you know, less clickbaity, like, I don't know, like STL and video games. But then you guys would have needed to go on my on the page and then read all that to know what the talk was actually about. And I mean, we all know reading is for nerds, so I saved you some time, I think, that way. I could also have gone like for something like STL, video games considered harmful, but I think I am not the right person for this talk. Anyway, so this video game programmer used the STL. We all know the STL, right? I still have a flare in my face, but just quickly, show of hands, who knows the STL or heard about it? Okay, you're my audience, I guess. Okay, so yeah, all comes back to the work of Stepanov a long time ago, proposed in '93, adopted in '94. I don't know what the committee is doing this day, but at the time it was efficient. Like all the STL, proposed, adopt, in the standard 1 year. Great. Offers, you know, a lot of generic containers, algorithms, iterators, the whole shebang. For people who are not like as old as me, this is what 1994 looked like. Just for frame of reference. Just another check. Who was born in 1994? That's not many hands. I feel old now. Congratulations. It made me feel old. Life. All right, so it has evolved since then, right? Like we had all the great books that Scott made about the STL and how effectively to use it. We even have a map of the STL, right? So it's literally not uncharted territory. We have a map. We know where to go. And then you move to the video game industry and you hear stuff like, no, we don't use the STL here. What? All right, so hello, the name is Mathieu. I make video games, yay. I make cool video games about history. And I talk about stuff on my blog, and not always build systems. So what are we going to talk to you with you about today? First, we're going to see the case against the STL, because there's been some controversies, to say the least, the past year or so against the STL from the video game community. So we're going to try to delve a bit into that and see if there is any point to all that noise. We're going to see a few containers in practice. Every time I give this talk, I cut some containers out of it because I run out of time, but we can talk about them after, don't worry about it. We're going to talk about some alternatives because, yeah, sometimes we don't use the STL and we have alternatives. And there's going to be a word about debug performance because that's one of the big things that usually comes back. What this talk is not about, because I only have an hour, questions included, so I won't talk about allocators or the problems with allocators. I won't talk about exceptions, and I won't talk about build times. You can bring questions about that after the talk or after the talk. We can talk about it, but I don't have time to this. So I'm just gonna sweep that over. All right, so let's go with the most obvious question. Is the LCL so bad? So what do we hear exactly when we hear people complaining about the STL? We hear that it's unfamiliar, you know, with those iterators, and why is it not just member function on containers? Like that's just weird. Maybe you just say like, but I'm using this platform and it doesn't support the STL. No, that's also a problem, right? Like you can't use it if you don't have it. We hear that it's bloated. You know, people, they keep adding stuff that I really don't need. And of course the performance is not that great. So let's go over one by one. So familiarity, it's probably the argument I have the hardest time hearing, because it's been 25 years. Some people in this room are younger than the STL. You had literally your lifetime to learn it. Also, it's not like it was just a one-shot thing and then we forgot about it. Like, if you look at the APIs of other libraries, popular libraries, Boost, Upsell, you name it, they kind of follow the same thing. So it's probably because these guys were onto something. And also, resources are plenty. Like, even at this conference, there's probably a bunch of talks about containers, algorithm, DSTL, all that stuff. We get that all the time. There's a million reference books, talks, everything is free. You can just, like if you have the internet, and if you're doing C++, I suppose you have the internet. If you're watching this online, you definitely have the internet. And look at the suggestion on the right. There's probably something about the STL and whatever. And I mean, the research from Alex that gave us the STL is sound. Like, I don't want to be the guy who has to argue against Stepanov that our approach to generates is wrong. I don't want to be that guy. I don't think I can. Maybe you can, and if you can, please do it, because there's probably something interesting, and I will just be like watching like two gods talking, but I just can't make that argument right now. Maybe, though, we need to be better at teaching it, because I don't know about you, but the way I learned C++ was the hard way. As in, I made a great UML diagram, and then I put a lot of inheritance of virtual classes, and I was super proud of myself. These days, not so much. I try to forget about these episodes. But yeah, what I'm saying is that, yeah, maybe we could be better at teaching it. We have the resources, maybe universities. I mean, that's a big topic that SG20 is working effectively on, and I think we're making progress. Availability is another concern, right? But major vendors have a reasonably good implementation of it. I mean, if you use GCC or Clang or MSVC, which is probably the vast majority, you have it. If you use consoles, well, the funny thing about console is that some of the SDK are under NDA, so you can't even talk about it. But I have from sources that they also use one of those. So you probably have it too. And I mean, it's software, right? As any software, yes, maybe it has bugs. And they should definitely be raised. And you should definitely talk to your maintainer or vendor to tell him, like, hey, your software is bugged, because your actual users won't shut up about bugs in your software. You shouldn't do either if you have bugs in the software you use. Just tell people about it. And of course, keep up with updates, because yeah, sure, if you're still on Visual Studio 6, yeah, maybe you have a few bugs. Also, and there's a more important issue, if your vendor is not able to provide you a good implementation of the STL, I would be worried about everything else he provides you. I'm not going to name anyone in particular, Oracle, but yeah, chances are, if you can't have a reasonably good STL given by your compiler vendor, I would be worried about the kind of code it generates. So yeah, consider open source alternative. Again, I don't have time to talk about some experience I had and how GCC was so much better even on a proprietary microprocessor, but it was. That brings us to the bloat. Because, I mean, and I'm kind of with those guys on the thing. I want to use some containers, some algorithms, some functionality, but it comes with a bunch of stuff I don't need. And I don't want to pay for it. And it kind of looks overcomplicated for what I'm trying to achieve. You know, like, have you ever tried to make a random number generator? I look up Merson Twister every time I have to do a random generator on the internet. I just can't remember it. But, I mean, the problem is, the standard has to work for everybody, and it's general purpose usage, right? We have to fit stuff from like from like video games, from like embedded to like huge servers, farms, and all that stuff. And it's kind of a hard position to make. Like, I'm not even sure Jean-Claude Van Damme could like be able to do that. Like, it's hard, but they try very hard, and I think they get somewhere. And sure, the design principle says if I don't use it, I shouldn't pay for it. In practice, sometimes you can't have 10 policies per class just to make sure that you can disable all the bits you don't want. And even if you had that, there would be a compilation time overhead because of all the SFINE magic that you would need to actually disable everything you don't need. With if context-parent concept is getting better, but still there would be a cost. So, yeah, for example, a big thing I keep hearing is that vendors have debug features, and I don't want to be helping debug features. I know what I'm doing, so why am I paying for these things? I don't want those debug iterators that are gonna warn me that I'm gonna compare two iterators from different range, or I'm gonna increment past the end. No, I know what I'm doing. I don't want to pay for this. Well, it turns out I can, because, you know, I almost promised on Twitter I would not talk about build. I lied. Sorry, there is this slide. Yeah, there is a build flag somewhere. a define, something that you can use to turn off most of those debugging features and stop paying for them. Also, and that's another thing, debug checks do not make no optimization. There is no reason why you can't have asserts and a reasonable number of optimization. CMake does it wrong, that's not why you shouldn't be able to do it. But since we're talking about performance, because that's the big thing, right? The reason why we care about, like we are worried about debug and extra features is mostly performance. We're doing video games, right? We have a time box. We have to render in X milliseconds, or there's going to be like jitter or freeze frames or whatever, lots of things that we don't want to see. So we don't want something unpredictable. We are worried about worst case scenarios and all that stuff. And there is a common wisdom to that, is that if you think about it, like the first thing that comes to mind is that the better control you have, because the lower level you go, the better control you have over performance, right? Because you don't have abstractions. You can just write pure raw C or C++, but mostly C. And then you're in control, right? You're low level, you're close to the machine, you know what you're doing, and you avoid all those abstraction penalties. That's the common idiom I keep hearing. Show of hands. Who thinks this is actually like true? That basically, yeah, the lower you go, the better control you have, and that's the way you go for performance. Come on, don't be shy. I know it's a C++ conference, but don't be shy. Okay, I can't see everybody, but okay, not many people. You see where I'm going, maybe. All right. So, sure, we come with a degree of abstraction. We have templates, we have iterators, we have checked iterators, we have proxy iterators. Requires a good optimizer to yield good performance. And if you want to, for example, if you want a good example, let's do a benchmark. I'm trying to just do a stupid accumulate function, right? I generate like 10,000 integers with a merchant twister that is hidden somewhere and I found on the internet. And then I just loop around the thing and just accumulate with a row loop. Like this is as close to the machine as I can do without going assembler. And then we do the same thing with the STL. So we run start accumulate. And then we bench it. And, yeah, that sucks. The STL is like 4.7 times slower. That is not good. If I try with a GNU implementation, it's a bit better. It's only 4 times slower instead of 5. That's still not great, right? I'm talking debug here, okay? No optimization whatsoever. So yeah, when you think about it, it sounds true. If you had abstractions, you're going to pay for it at runtime unless you optimize. It's going to be slower. So yeah, sure, go closer to the machine, then you have less problems. And that's why this guy comes and he's like, that's why I use C. C++ is so bad without optimization. Like, nah, just forget it. So let's go back a bit to 1994, which is an interesting year. For example, it's my 10th birthday, so it's obviously an interesting year. But do you guys know what this is? Show of hands. Okay, so I guess it's the same people who are older than 1994. So it's a great 486. Do you guys know what's so great with the 486? What's the thing with 486? What? Not at the, sorry. Yeah, that was it, but no, that's not what the thing I was leading to. But it had a math core processor, yes. No, the great thing was, it was a simpler time. Because that's the last CPU that did not do out-of-order execution. That is the last time your CPU, when you wrote C, just as the dumbest way possible, executed the instruction one by one in order, waiting for whatever fence, memory barrier you would hit, without trying to do anything else, even if it was completely unrelated. 1994, most of you are older than this. Most of you have never had to program against a CPU that actually was sequentially executing instructions. That's the thing. Your assembler is lying to you. Your C is lying to you. What you're writing is not what's happening. Your CPU is trying to do out-of-order execution because turns out it's much faster. And so here comes the question. How is that important? Like, if I write row C, that gets translated as the pure row assembler I think it does. That is being made for my great serial, not out of order per CPU. Shouldn't be too much of a difference, right? Anyone want to guess if I take the same algorithm I show right now and I enable optimization or not on the C version? Anyone want to guess? Is it going to be like the same ballpark? Is it going to be faster? Yeah? Yeah, I mean, at least it's probably going to try to vectorize. Sure, so at least I expect like 4x, right? Something around 4, maybe 8, depending on what SIMD I have on my CPU. Because, you know, my dumb C does not actually use a SIMD, but my optimizer might be able to. So 4 to 8 times, that sounds about reasonable, right? So let's try. I write this great benchmark, and then I abuse a lot of quick bench. Sorry, Fred, it's not the worst I have been doing yet. And I just tell Clang, just don't optimize the instruction for me, and just put the same one in the same bench. Oh. Wow. Turns out I have no idea what I'm doing with my row C. If my compiler doesn't come to my row pure C and actually save me from myself and completely reorder what I'm meaning, I get 26 times slower. Sure, if I manage to vectorize manually, I can probably get 4x better. So it would be like, oh, I'm bad at math, but something around still 6 times slower. So yeah, as it turns out, yes, C++ is slow in, oh, sorry, spoiler warning. C++ is slow in debug, but C is not that better. I mean, sure, it is better, but it's still terrible compared to what you actually get. Like, you have the illusion that by writing row C, you get closer to the metal and get the best out of it. No. Your compiler gets the best out of it. You're just playing a losing game. And actually, since I like to torture quick bench, I managed to do a benchmark with different level of optimization in the same translation unit. I'm worried of sharing the code because of what people will make with it. But here is the idea. You have OJ, which is minimal optimization for debugging with GCC, both with the row C version and the C++ version. And as it turns out, the C++ version is faster in OJ. And then you have the row C pure version without any optimization whatsoever. And then you go on and on and on. And O3 is when vectorization kicks in. So you see another boost of performance. But the thing to remember is row C is terrible if you don't optimize it. Row C++ is even worse. But if you just turn the minimum optimization from your compiler, you can even beat C. So, yeah, that's basically what I just said. C++ abstraction will be slower than row C, but actually both C and C++ are stupidly slow compared to optimize really the builds. We are very far away from our 1994 processor. We really, like, you need a PhD in or two to be able to write good assembly for a CPU, and turns out your compiler is made by several PhDs, so it knows how to do that, and it knows which version of the CPU you have, and how in this particular case it's going to do something better. Sure, you may be smarter in some cases, but on average, even if you go row C, it's just going to, like, don't show up. It's just going to be a completely one-sided. And again, minimum optimization, enormous gains. So, like, if you're working on GCC, OG is going to save you by a huge margin. And then, yeah, we get into the area of compilers and actual vendor optimization. Some are good at it. GCC is good at it. MSVC has some knobs you can turn to get okay performance and still be able to debug it. They have made a lot of efforts to be able to debug optimized builds. There's probably some room for improvement. I mean, just ask Chandler about O1 on Clang, and he's going to tell you that it's slower than O0. I bench it, it's true. Know your build flags. Oh, sorry, that's the second slide about build. Anyway, let's talk a bit about those containers now. So, again, I need to cut slides every time I rehearse this talk, so I'm just going to try to focus on the most used containers. So we're going to talk arrays, we're going to talk dynamic arrays, we're going to talk associative containers, and we're going to talk hash tables. That's basically the big 4 things you use. I mean, you guys know you shouldn't be using lists, right? Good. So let's talk about vector. We all know vector. We all love vector. It's a heap allocated array that can be resized. It's the go-to container in the STL. I think it's probably what people say more and more, like, if you don't want to think, go for vector. Even if you don't want to think a lot, still go for vector. It's cheap to move, it's cheap to random access, it's as fast as it gets to iterate over. And the big reason is, and I think I'm not the first one to tell you this, is caching. Because again, your CPU is not a 486 from 20 years ago. It has a lot of cache. Because it turns out accessing RAM is slow. And I'm going to highlight the important part. Thanks for ITR for these graphics, by the way. If you're going from register to register, it's basically one cycle, maybe even less. I don't even know how you can make less than one cycle, but they managed to. Congrats, CPU vendors. That's magic. If you hit something that is in level 1 cache, it's going to be, I don't know, like 3-4 cycles. Still slow, but acceptable. And then the further down you go, the worse it gets. And if you have to hit main memory, this graph is like 2 or 3 years old, you're going to be waiting like 100, 150, 200 cycles just to get your data and continue. That's a lot. And that's why we like vectors, because everything is contiguous in memory, and you're constantly, or most of the time, eating L1 cache, which is mega fast. And that's great. And since we have so much of an impact, of course, the big takeaway is that sometimes big O is lying to you. Sometimes you do a linear operation on a vector, and it's faster than a logarithmic operation on another container because of caching. Because you're starting with a factor of 100 as a penalty. So yeah, if you have a small set, and small sets may vary, you might have to bench it. Brute force through a vector will be faster than like a map or whatever. And again, another quick suggestion, if you're doing like a read-intensive associative set, but you only read it, consider sorting it. Just sort your vector and just do a linear search to it. It might be faster depending on what you're doing. Some hash table will manage to do better, but not all of them. Of course, if you need to keep references to elements in vectors, prefer indexes to pointers, because when you push back something, it might reallocate and move your stuff away, whereas your index will still be valid as long as you're pushing at the back. Just small ideas, but what are the limitations? Because we're not here to talk about how great vector is. We're here to talk about limitations that we as video game programmers find in the STL. So what are the limitations of vector? There's none. Vector is awesome. I love vector. It's great. Okay. I may be biased there. No, I can find some limitations. The growth factor is not specified by the standard, and it's not configurable by the standard either. And most implementation will not allow you to change it. And there's been a fair deal of research by people who do math, which I don't understand, that says that 1.5 is very good and 2 is not that good, and it has relationship between Fibonacci and other stuff and the golden ratio. I have no idea what it means. But the gist of it is, some research suggests that 1.5 is better, and you can't control it. That's not great. Also, by standard specification, you cannot do small buffer optimization. And allocation may be costly, because on worst case, on an allocation, you might have to go to the operating system to get RAM, and the operating system might have to start doing swapping, and maybe will schedule your process out while it's doing that, and then it's gonna just stop forever. Well, I mean, as long as cycles are considered, it's gonna be forever. So we might want small buffer optimization, which basically means every time I allocate my vector, I just allocate a bunch of elements immediately in the same go, especially if it's on the stack, and then I don't have to pay for that completely unpredictable allocation. And that's great, but the standard prohibits it. Because the standard says if you move a vector, you don't invalidate references. And you can't do that with small buffer optimization, because you're actually gonna move the bits. And let's not talk about vector pool. Just, I would say forget it exists, but no. Remember it exists, and you should not use it. So what are the alternatives? The big one, of course, is small buffer optimization. Boost has one. Facebook has one. Google has one. It's great. It avoids heap allocation for small sizes. You can specify which size. Yeah, just remember that it might be a linear move and not constant, because you actually have to move the bits from one vector to the other. So depending if you make a small vector of very big objects, you might actually notice something. If it's small object, sure, go for it. I don't think there is a paper on this, or there might have been one at some point. I'm not sure where it's going now. But if anyone has something to suggest, just come to me after. There's array then. Array is like vector, except it's fixed size. At compile time, you say, okay, I want an array of X elements. It's come from C++11, but I mean, who is not using C++11 here? Come on, are you just shy, or is it literally nobody? Wow, time flies. Great. So it's great because blah, blah, blah has the same properties that, that vector has in terms of cache and random access. And yeah, you have to move all the bits every time you move it. So remember that it's not because it's moved that it's cheap. And that's the thing I'm trying to hammer on here. Move doesn't mean free. It might mean cheaper, but sometimes it's not. Sometimes it's as expensive as copy. The biggest problem with array that I usually find, and I think I'm not the only one, is that it's fixed size and not capacity. And there is a couple of use cases when you say, I know I'm not going to be more than like 60 elements or 100 elements at one time, but I'm not going to allocate all of them now. Sure, you can try to put like sentinel value and remember how far you got, but that's just messy. What you would like is clearly to have a stud array that just starts with zero capacity, with X capacity you set, but zero size, and then you can push back in it, and then you can pop back in it. And yeah, stud array is not suitable for any kind of dynamic insertion, and that's just not great. So we want a fixed capacity vector, basically. Boost has one, STL has one, Facebook has one. And actually, someone proposed it to the standard. I'm not sure what's the status of the paper right now, but there's a paper on it, and I think it's still moving forward. So hopefully, we will get it at some point. The name is static vector. I don't like it, but that's just me. Now let's talk about maps and sets. Because vector is probably our bread and butter, but then the next thing we have is index search, because we want like fast lookups. So map and set, classic sorted associative containers. You want some mapping, and you want it sorted. It gives you usually a logarithmic time on access, insertion, and erase. It keeps iterator valid even if you remove everything else. Like, as long as you don't remove an element, the iterators stay valid. You can put as much as you want in it. Reference stability might be good, especially for newcomers, people learning C++ or others, because it's, well, you're much less likely to shoot yourself in the foot. And since everything behind the scenes is just allocated somewhere, it's a one to move, so again, cheap to move, and we like it. But it's almost always implemented as an RB3. And that's really not cache friendly. I mean, if you're lucky, if you have the right platform and you fill it in one go, chances are all your nodes are going to be stored contiguously in memory because you kept calling the same allocator over and over again with the same size. And possibly just keep chaining your data over and over. So if you access one node, the other nodes that you inserted might be close in memory. Might not be sorted close, but they might be close. But still not great. And especially if you have something that lives a long time in memory, it's not cache friendly at all because there's no way you can predict where the data is going to be every time you jump through one of the sons or parents of the nodes. And of course, it's still logarithmic and not constant, and I want performance. And 1 is better than log n. I think maybe there's some exception, but I'm not good at math. As long as n is better than 1, I guess it's true. Whatever. So yeah, nah, this guy again. It's like, no, they have terrible performance. Please don't use them. Can we do better? Can we do better than this terrible RB3 that has very bad cache coherency and all that stuff? Well, actually, not really. Because by standard, there is a bunch of constraints that are there. The standard says, if you insert something, you don't invalidate anything else. If you remove something, you don't invalidate anything else. It's basically impossible to do without a tree. You have to have some kind of structure that will not reallocate and move other things around. You can try having a custom allocators, but I say I'm not going to talk about allocators, so let's just waive that for now. But if we start dropping constraints, now it gets interesting. For example, let's say it doesn't have to be sorted. Because the minute it doesn't have to be sorted, I can start using other structures. I don't have to use a tree. I can use a hash table. And that's exactly what we have. It's called an ordered map and an ordered set. It's great. It's average constant time on insert, erase, and lookup. And we're getting close to what we wanted. Oh, this guy again. Yeah, because there's this thing, you know, that's called open addressing, and it's like, it's the gold standard of the hash table. And if you don't use it, just go home. Like, nah, just stop making computer science. I'm just kidding, but that's the kind of thing you might hear. Because, yeah, I want the best. I don't want second best. I want the best. So sure, you can get better performance with open addressing. There is a bunch of papers on that. There is a bunch of hash table public implementation that use it. Google has one. Others have one. It works great. But actually, it's incompatible with the standard again. Oh, those damn standard people. Why did they do that? Why do they keep blocking performance? Well, actually, it doesn't come for free, because nothing is free. Chandler told us that a couple of days ago. There's a high time and space trade-off, space trade-off to do. Because if you do open addressing, I'm not going to make all the demo here, because I don't have all the time, but we can talk about it later. But the biggest idea is the load factor, the optimal load factor for an open address hash table is much lower than a bucket list-based hash table, which means on average, you're going to waste much more memories with empty slots. So sure, that's a trade-off, and maybe you're on a platform that, you know, memory is just free. You know, you're running some kind of server cluster and memory is just a number. Sure, then go for it. But some people actually have to pay for that memory. Some people have platforms that don't even have swap. And they just don't want to afford that cost. And also, open addressing usually means you're going to have, even if you don't rehash, you will break reference stability. And again, that's something that might shoot people in the foot. And also, and that's the biggest thing I think I discovered when I researched this talk. Caching, because open addressing is supposed to be faster because of caches, because you don't have to use bucket list, and so you have better cache coherency, blah, blah, blah. That is not even the first and the biggest reason why some STL implementations are slow. It has nothing to do with the standard. Just don't use modulos. Just quickly, when you hash something, you have to match it to a bucket. And then the common and maybe naive idea is just to do a modulo of the size of your hash. But as it turns out, oh, I forgot some slides somewhere. But modulos are super slow, as in a lot of cycles. And a lot of cycles that are blocking the next memory fetch. So very slow. And you don't have to use them. And as Malt showed at CPP now, I think it was last year. I'm glad I have the date there. Microsoft does this right. The Incomeware, which is the implementation of the STL that Microsoft uses, it doesn't use modulos. And guess what? It's actually reasonable in performance. Clang and GCC, maybe don't use modulo. I could talk a lot more about this, but Malte just do it better than me. And there's this technique I learned recently that is the technique of the pros, which is at some point just insert a reference to another talk and then continue. So watch his talk. It's great. It tells you everything you want to know about hash tables and how you can even get more performance if you are okay with even more trade-offs, and how easy implementation, if you have to be stuck with Linux or GCC or Clang, can give you reasonable performance similar to Microsoft's implementation. But now I want to talk about the STL and new online. Is the camera there? I hope it is. Else I would look really silly. Because here is the kind of tweet that started this talk. I'm paraphrasing because I don't want to name anyone in particular. But yeah, this is the kind of thing I can read on my Twitter sometimes. That is not okay. First of all, and that's usually the first thing people reply, committee makes specification, not implementation. That might sound like a cop-out, but it's actually how it works. And that's the rules. The standard makes a standard. It's a reference, it's a specification, and people implement it. You're blaming usually people are blaming the wrong person when they're going for quality of implementation. Because some people in the committee happens to be compiler vendors or work for compilers vendors, so they actually implement it, but that's not most of the people, and that's most of the time not the people who push the paper to the committee. Also, C++ is a general purpose language. We have this tendency of saying, why is not my use case the only use case that matters? Well, because we all have use case that matters, and at some point we have to do something that is okay with 99% of the use cases. And that means, for example, that we will not make trade-offs that are way too expensive for some people. And that, for example, is the reason why the hash table is not using open addressing, even if there's research that suggests it's faster. Because that's a huge memory trade-off, and you can't impose that on everybody. And I don't know if I should have to say this, but a social media rant is actually a very bad way of getting your point across. Believe me, I tried. Is anyone following me on Twitter? Okay. So let's talk about burden of proof for a second, right? People use the STL every day. I don't know, do you have a phone? I mean, of course you have a phone. Like, I have one, it's Android, I think, yeah. So basically it's Clang. If my phone works, I guess Clang works. And Clang's STL works. And my laptop works, and I think it's made by Microsoft, and I think they probably eat their own dog food, and everybody in the world uses Clang, GCC, and MSVC on a daily basis, and if there was a huge problem, there's a huge chance someone would have noticed this. I'm not saying there is no issue. There is issue. Every software has issue. Nothing is perfect. All those jokes against Microsoft or whatever, they come from somewhere. There used to be some problems. No software. I mean, I don't make software that is perfect. I don't think anybody does. Sure, but the burden of proof is on you because the rest of the world is just using the software and it kind of works. So if you start saying stuff, and that's the thing I hear usually, it's like, oh, no. We found a bug somewhere in thread or in array or in vector or whatever. No, it's just bad, it's bugged. We have an alternative. And then you ask, but what was the bug? And they're like, we don't remember. But at some point, some year, there was a bug. Do you know the story about the monkeys? It's a social experiment that was done a couple years ago. Probably 10 or 20 years ago. They put some monkeys in a cage, and there was like a banana that was coming up from the ceiling, and they could grab it and eat it. At some point, they introduced a new mechanism with like some kind of camera, or I think it was manual, I can't remember. If a monkey grabbed the banana, everybody would get sprayed with some kind of jet water. So the monkey quickly learned that they should not grab the banana, that it was a trap. And then they started slowly introducing new monkeys and removing the olders. And of course, when a new monkey come up, doesn't know about this, and try to grab the banana, all the other monkeys jump on him and say, no, don't do it, it's bad. And so what they did is that they waited a couple, I'm not saying generation, but they replaced all of them over time, up until the time that there was no monkey that actually had seen someone grabbing the banana and getting sprayed. And then they disabled the mechanism. And then they introduced new monkeys who tried to grab the banana, and they got bashed the hell out of it because you don't grab the banana. Why? Nobody knows anymore. But you don't grab that banana. And that's the same idea. It's like, yeah, you don't use thread because it's bugged. How is bugged? I don't know, but this guy told me it was bugged. If you find a bug, there might be one. Sure, report it to your vendor, right? But also, if you need to fix it and you can't wait for an update or you don't get an update, make a test somewhere that shows that there is a bug in the STL and that your implementation passed the test and the STL doesn't, and revisit it from time to time. Don't be the banana eating monkey. That's just not good. Because, yeah, people fix their bugs. Also, the STL has to be good enough, which means it cannot make unsafe assumptions, reference stability, memory of it. I said that before. We target, the standard code targets the most common use case. So it has to make some decisions, and maybe you disagree with the trade-off, and that's okay. Specific cases can benefit from specific implementation. Of course they can. That's the basis of computer science. If you have a very specific use case, you can make some trade-off decisions that a generic implementation can't. And I'm not going to stop you, and I should not stop you. Do it. But remember the corollary. If you make a fit-to-purpose alternative for one specific case you once encountered, it doesn't mean it's going to be great for every other cases that never had the problem in the first place. And as Donald Knuth once said, the real problem with programmers is that we spend far too much time worrying about efficiency at the wrong place and at the wrong times. Basically, the idea is there is a good reason for an optimization in a specific case. That doesn't mean it should be the default case for everybody else. I've seen too many people say, oh, I have this one corner case in this case where a small buffer vector is better than vector. So now the code standards say you don't use vector. You use small buffer vector everywhere. It's a bit too quick on conclusion, I would say. And finally, I would talk about engaging with your peers, because I mean, we all have sometimes things we want to say. It's fine. But usually, ranting on C++ on Twitter doesn't make C++ better. Sometimes you make jokes, and they become great things. I mean, we have a guy in the room, he made a joke once, and now we have include C++, that's great. And sometimes people make a joke, and I end up making a talk. And I mean, I'm not saying it's great, you will tell me at the end. But it's great, I hope. Also, if you give a talk about a problem, please don't give it at a conference that I am totally not naming here. That is a good conference, but has every and all of his video behind a paywall. Because most of the people here and at the committee will not see it. Make sure that your voice is heard where the actual C++ community is and where the people who can do something about it or decide to help you doing something about it can hear it. Go to meetups, go to conference, go to his ISO study group. SG14 is open to everybody. Basically, if everybody collaborates, we will make faster and better progress. And the bigger the sample, the better results. When a paper is pushed through the committee, the bigger the sample of people that are consulted is, the better we will be sure that actually the thing is sound and everybody is okay with it. If you rant on Twitter and then don't go to committee meetings, yeah, sure, nobody's going to hear it, and your argument will not be heard, and maybe decisions will be made that are actually not bad, not good for you. If all of your money depends on C++, maybe you should try to have your voice heard on C++. So yeah, don't be afraid of talking, and I'm not just saying that for video games programmers. That's true for any field. We have this unicorn syndrome sometimes of thinking that we have problems that nobody else has and nobody else can solve. Most of the time, it's wrong. I can tell you, I've been in 3 different industries, and I've seen that all the time. You bring your expertise, and they're like, no, you don't understand. You come from another place. We have very specific problem that nobody has. Everybody has performance problems. Everybody has memory problems. Everybody has that shitty compiler that they have to work with, performance problem or compiler problems. I don't need to work with a PlayStation to have problem with my compilers. I work with Sun. But don't be afraid, and that's the big thing. We should not stop from challenging quality of implementation. Because, sure, as I said before, it might seem like a cop-out to say, oh, the committee is not responsible. But someone has to be responsible for quality of implementation. Do not be afraid of holding your compiler vendor or whatever vendor you have accountable for the performance of something he does. But if you find something, if you find that actually, I don't know, we had a bunch of examples in the past days about a couple of features in in the STL on most vendors that were actually clearly badly optimized and could do a lot better. Publish your findings. Just don't write a wrapper or an alternative inside your company and tell everybody to use it. Publish it. Provide benchmarks that everybody else can use. Because if there is a reference benchmark of, I don't know, vector, map, function, whatever, we can have like the acid test that we had in JavaScript for CSS for so long. And we can run it all the time. And then you can everybody can see that this compiler has an issue. And that probably should be fixed. Because the minute there is a contest and everybody wants bigger number, things will get better. That's just how we do. We love a challenge. Oh, and if you need that packaging, you can ask me. I'm the guy who talks about package management all the time. So, yeah, to conclude, the STL tries to be a good enough default for everybody, as long as some and it will be, as long as some optimization are enabled. If you go full debug, you will be slow. You will also be slow in C, but you will be even slower in C++. Sure. If you have a specific case, and you can drop some constraints from the standard, you will get better results. And you should. I'm not telling you not to. There are great libraries out there that do it. You can think you have a better case, you have a specific case that is not covered and you want to make your own. Go ahead, go wild. I'm not going to stop you. But feedback is needed to improve the experience of everybody. So if you have a use case, make your voice heard. If you have a benchmark that proves that an implementation is bad, make it heard, publish it, tell other people so that it can actually be fixed. Because instead of fixing it for you in your old code line, you can fix it for everybody else. And that's not a much bigger effort, as long as it's like what, 2 git push and a tweet? It's not too bad. Oh, and furthermore, I think your build should be destroyed. Thank you. And we have 12 minutes for questions.
Great. I have a quick question. Do you see examples of more and more video game companies adopting the STL? Do you see a trend for more people using STL in video games?
I'm sorry, can you repeat that? Because I have some echo and I'm not sure I got... Sorry?
Let me come back.
Yeah. Come here and I will repeat your question on my mic. Yeah.
Do you see a trend for more and more people in video games using STL?
Do I see a trend of more and more people using the STL in video games? I don't have enough data to answer. I can tell you that I'm pushing people at my company to do it. And since my tech lead stopped reviewing my commits, I guess it's getting faster and faster. But no, I can't answer for the whole thing. I hope it will, because I think there is more and more talks about it. But I don't know, maybe I'm not the best person to answer that. You're welcome. Another question? You might have to yell it because of the feedback, but go ahead. Well, question? Great. So the question is it okay to make dynamic allocation in game logic? I'm not saying I'm right, but I do it all the time. There are better, this is not a talk about allocators, but yeah, you might have to allocate some stuff sometimes during your game logic. You might have to allocate stuff at some points, and you might need a way to do it. There are allocators, there are strategy to pre-allocate that kind of things. Usually what you want to avoid is going to the system allocator, because unpredictably, you can hit, like as I say, like out of memory, let's go to the system to ask for memory, and then the kernel has to page out, and then it takes forever. And you can't predict when it's going to be happening, and you sure as well won't be able to debug it. For my use case, it's used to be good enough. I'm not saying we're the poster child of AAA performance, but my games are mostly CPU bound, and we manage with dynamic allocation. Allocators would probably make that better, but it also requires some thinking. There is a great talk about allocators that was made by Andrea Weiss at ACCU. I encourage you to look at it. He looked at the different options. You can probably also grab John Lakos, which is, I don't think it's in the room, but I I saw you at CppCon. He's the guy about allocators. He can probably tell you more about this. Does that answer your question? Perfect. Question? You like the monkey stories? Oh, really?
Somebody told me the story.
Right, so someone is telling me that it's a story. I mean, yeah, maybe it is. I didn't know about that. Okay, so the monkey story is not true. It was a lie all along. It's just a story. But you believed it, right? Yeah, check your data. I should.
Hi, thanks for the talk. Really nice talk. I actually wanted to answer the first question. So I work in video games for quite some years now, and in reality, it's never like a yes and no. Kind of use the STL or don't use it. It's a bit of a mix. So normally, game dev comes with like large engines, like Unreal Engine or like Unity, that they have their own containers that you use for like the majority of the tasks. But that doesn't mean you cannot use a vector or a map or a thing here and there. So it's a, like always the question.
Trade-off.
Yeah, trade-off.
Yeah,
as like a mixed kind of thing. It's never like we hate it or we love it.
Yeah, I think as I said, the remark was that usually in video, like for example, in this person company, the thing comes when in some cases they use the STL and in some others they don't because there is a better alternative, and that's exactly what I'm saying. Good enough, maybe sometimes it's fine, and maybe you have a specific case that warrants something better. Maybe you have like a place when you need small buffer optimization because most of the time you will not allocate enough to need to go to the heap and it's much faster. Maybe you can actually afford to pay the penalty for hash map and you want to use open addressing. And I think it's good.
I was wondering, what 14, 17, or 20 features do you see have most effect in the video game industry?
What features of the new standards do I see have the most effect? In terms of STL, I really like 17 variant because it's just a better union. I like what 11 bring with the new array. In 20, like especially about containers and performance, I don't know. But in the future, we might get linear algebra from Guy, which is something we really want to have. We have the paper about the fixed capacity vector. That is something we really want to have. I don't think we're going to have a map 2, because that flat set. There is going to be a flat map and a flat set. I should follow more. A guy is telling me that there's going to be a flat map and a flat set. So if you actually want open addressing, there will be a reference implementation available to you if you can pay for the trade-off.
Thank you.
Oh, and I think we were going to have dynamic beat set, or I'm not sure it's done yet. 23, good.
Hi, thanks for the great talk.
Thank you.
Just wondered, did you try to compare standard STL implementation and some other implementation like EA STL, and how did they perform?
No, for this talk I did not. I think there will be differences because EASTL is not 100% conformant to the standard from what I remember. For example, I'm pretty sure they don't handle exceptions, which obviously will yield some difference. I should definitely try to benchmark it and see the difference. There is, and as I was saying, there is a need for having a reference benchmark for most of the features we use to make sure we held our vendors accountable for the quality of implementation, instead of trying, because blaming the committee is not going to help anybody. What is going to help is if we have actually some of those benchmarks that says like, hey, here is the benchmark, and it shows that a bunch of people's implementation are faster, like that what Matt Malte did, for example, for his hash map implementation.
Thank you.
We still have a few minutes if anyone else has a question. Yes? right. Question about what tools you can use to know about performance. So yeah, of course, when I research talks, I usually use Quickbench or stuff like that because it's very practical to have a micro benchmark. But micro benchmark are just going to just show you some things, and I think that might be one of the issues, is that how do you reduce the case in your game to a micro benchmark? And I think this is where it gets tricky. Personally, when I have like a huge performance bottleneck and I want to find it, I start with something like VTune, or even the Microsoft provided profiler is okay to get some kind of a ballpark number. I think VTune is a bit more, give you more data. You can see stuff like cache misses or back-end, front-end, bound instructions and all that stuff. That usually helps me. But at the end of the day, I think what would help us is having more benchmark with more data. It's not going to be like one benchmark that you can fit on a slide because there's going to be a bunch of tests. But that's the thing, when I researched this talk, I didn't find a lot of benchmarks. And that's where I think we need to, again, be better. And yeah, the best idea I would have is that if it's container-based, that if you manage to find, like if you go with VTune or whatever, and you find something that, because you're going to have to prove where it comes from, right? Like you find a bug, or you find a VTune, or your profiler tells you there is a bottleneck somewhere in your code. At some point, you want to have to blame somebody, and you will end up saying, oh, this is because this container is generating like bad code or whatever. You can probably take that and reduce it to a structure that is similar to what you're actually doing, and then get something that will help you working on. And you're probably also going to make much better progress working on a small benchmark than actually rebuilding your whole game all the time when you change one container. Because I don't know about you, but if I change one standard container in my game, I just have to rebuild everything. And that's just not really an effective way of iterating over. So you probably want to isolate your problem first once you located it. And then the next step is to publish that benchmark. Does that answer your question? Perfect. And with that, I think that's all. Thank you.